I want to do more proofs. I know I told you we're going to move on, but we need to learn how to do a proof by mathematical induction. There's a fun technique that will come up in calculus in a few places. So I want to do that first. If we have time at the end of the class, then we might do like a proof why that divisibility by 3, that fun rule. That's a fun rule. We might prove that. That's actually not that bad. But first, I want to talk about mathematical induction. Because it will definitely show up in Calc 1 and in Calc 2. I mean, you'll see us do that. So I will start with a very famous problem, and I'll ask you to add all natural numbers from 1 to 100. That's a fair question. There are a few ways of doing that. And the straightforward way is actually go, okay, 1 plus 2 plus 3 plus 4. It'll take us how long? And if I take a calculator away, now who knows the trick? Well, I mean, I can express this using the summation symbol. I'm glad you're bringing that up. So let me show you how to, because again, we're going back to how much we dislike writing long sentences. Because I can express this in a very precise way. There is a so-called sigma notation. We use it to represent sums. So I'm just going to use it to express this sentence, and then I'll tell you what it means. So here's the sigma notation. This is the capital Greek letter sigma. And what we're just adding a very simple item. So just 1 plus 2 plus 3 plus 4. So just basically we're adding a whole bunch of n's or i's. You can call them whatever you want. There are no extra math. We're not squaring anything. We're not square rooting anything. We're just adding. So this sigma just says add a bunch of these things. Just a single items. The lowest value of I is 1. So we're going to write it here, I equals 1. The highest value of I is 100, so we put it here. So all it says, add these expressions starting from 1 to 100. So we read this as 1. It starts at 1, then it increments, becomes 2. Increments becomes 3, all the way to 100. That's what this notation means. Does that make sense? You kind of have an algebraic expression, and then you put conditions on your variable. What the lowest value of the variable is, what is the highest value of the variable is. So this long sentence can be expressed. You don't need that little box around the I. It's just me doing something else there.
So that this could be expressed as the square line of 100, and that just means 1 plus 4.
Yeah, so that's the capital sigma. So for example, here's another one. Add consecutive squares from 3 to 17. So I can express it like this. So consecutive squares, so I'm squaring things now, right? The lowest value of my variable is 3, so I starts from 3. The highest value of my variable is 17, so it goes all the way to 17. So that's 3 squared plus 4 squared plus 5 squared, all the way to 17 squared. Now, this thing in no way helps us to do the math. It just helps us to write it in a concise way. And you'll see a lot of this notation in Calc 1 at the end of Calc 1, and there's going to be all over Calc 2. If you go that far, okay? So for now, this is just notation, okay? So it's called sigma notation. We use that. It's a capital Greek letter sigma. We use it to represent sums. Okay? But going back to our problem, let me go to the next page. So we're trying to figure this out. So does anybody know how to do that fast? Have you heard about this problem, adding consecutive? So there are a few mathematicians. Yes? Yeah, exactly. Very good. So this story goes back to this mathematician, Gauss. Have you heard that name? Friedrich Gauss? It's one of the names you should get familiar with. It's probably in the top 3 mathematicians of all time. And there's a famous story when Gauss was a very little Gauss. He was in a classroom and the kids were misbehaving and the teacher was like, oh, guys, just add every number from 1 to 100 while I take a break. And that's back in like 1700s. So Gauss was like, well, clearly it's 5050, being, 8-year-old Gauss. And the teacher was like, what? How did you do that so fast? And that's what Gauss did. He's like, well, if you list all the numbers that we're trying to add, if you actually put them in the list, and then you go, all right, first number plus the last number. What is that sum? 101. Well, then you take the second number and the second to the last number, 2 and 99. What is that sum? 101. And then you just keep going in this fashion. 3 plus 98, 101. 4 plus 97 is 101. And then you just keep going till you get to like what? 50 and 51? You always get 101. Well, how many of these 101s you think we're going to get if we meet in the middle? 50. So this whole sum really becomes 101 times 50, which is 5050. Okay? So the actual general formula that comes from here, the sum of consecutive natural numbers is given by the formula n times n plus 1 over 2. So in our case, when we had 100 for n, so it's 100 over 2, that's 50, and then 100 plus 1, that's 101. So using this formula, you can add any consecutive numbers. So for example, if you want to add numbers from 1 to 132, so they'll become 132 times 132 plus 1 over 2. So that's how that formula works. I mean, we do need to know this formula, which allows us to do those summations fast. So what is that going to be? 132 divided by 2, is that like 66 or so? So this becomes 66 times 133. Now whatever that is, that you can plug in a calculator. It's a much simpler computation. So, oh, that's a pretty number, 8778. What do you call those numbers? You know, like we were all excited about the year 1991 and then 2002. So we gotta wait a while now, right? When is the next year like that?
2003.
No, 21, 12, I think will work, right? What? Yeah, 2112. We gotta, I don't think we're gonna make it.
2020.
Nah, because this has to be, you know, mirror. Anyways, a side note. There is a name for those types of years. So do you understand how this formula works? So whatever this n is, it's that number times the next number plus 1 over 2. So here's an example. From 1 to 132, so it's 132 times 133 over 2. So it makes the addition really fast. Okay? Well, what we're going to try to do today is to actually prove these types of formulas. Because, I mean, this is, well, is it going to work every time? How do we know that? Because that's the big hang-up. We like doing things like that. So here's an idea behind mathematical induction. If I go back here, so the mathematical induction works in the cases, especially works very well in the summation cases, but it works in the cases where there is such thing as the smallest value of the variable. So you see here our variable is bounded by 1, because we're looking at natural numbers. We're not allowing negative numbers, so the smallest natural number is 1. So you always have that case. So here's the logic. This is how people thought about this proving techniques. Let's prove that our statement, which is this statement right here, works for the very smallest value of the variable possible. So in this case, I equals 1. Okay? So let's just show that this statement works from 1 to 1. Is this going to hold true? What is the sum of natural numbers from 1 to 1? 1. If I plug in 1 for n, is that going to work? 1 plus 2 over 2. Does that equal 1? Yeah, so that works. So all you show is that it works for the very smallest value of the variable possible. Okay? So we call this the base case. And that's the easy case. You just plug in that number, see that the formula works. Now the next step, we'll call this the induction step. And that's how that step works. You assume, and we always like to do that, we assume that the statement is true for some number here. Let's call it k. So it's true for some k. So with that assumption, if it's true for some k, show that it's true for the next step. If it's true for k, show that it's true for k plus 1. See, that's what you accomplish. So then, therefore, if it's true for 1, then it's true for 2. If it's true for 2, then it's true for 3. If it's true for 3, then it's true for 4. And then it unravels all the way through all natural numbers. Does that logic kind of make sense? So you show that it's true for some case, the smallest case, and then you show that it's true for something, then it's true for the next number. So if it's true for 100, then it's true for 101. And then it basically rolls out through the whole natural number set. Does the logic make sense? Kind of? Okay. So let's write out the strategy. So to prove that proposition, and let's call it P of n. So this is, here's P of n. That's what I mean by proposition. So for some n, here's the statement. So we'll, use that notation for a minute. We need to follow two steps. First, prove or show usually is just plugging the number in that P of n is true for the smallest value of n. So we'll call this the base case. And usually you know the smallest value of n every time based on the problem. If they tell you that something is true for all natural numbers from 3 and above, then 3 is your smallest value of n, and you show that that case works. And the second step, and that's where the money is, and that's the hard step, we're going to assume that proposition is true for some k, meaning p of k is true. So we're just going to assume that. And then we have to show that p of k plus 1 is also true. So this is called the induction step. So again, what allows us to assume that the proposition is true for some k, because we already showed that it's true sometimes. The base case allows us to make that kind of assumption. And then basically you start from the base case and you get it covered for all natural numbers. Is that okay? So that's the idea. So let me show you an example. Let's just prove this proposition right here, that the sum of n consecutive integers or n consecutive natural numbers is given by the formula n plus 1 over 2. So we're going to try to do that by mathematical induction. So prove so we're going to do that proof by mathematical induction. We just say induction. You don't have to say mathematical. So here's the first step. We have to establish the base case. So that means n equals 1 in this case. This is the smallest value that variable can be. So if I actually use the sigma notation, I goes from 1 to 1 of I. Well, that's just 1. There is no other number to add, so the sum is 1, right? But at the same time, if I plug 1 into the right-hand side of my proposition, if I plug in 1 times 1 plus 1 over 2, that becomes 2 over 2, that also equals 1. So that works, right? These two things give me the same result. That makes us happy. That's the base case. That's it. The base case is usually really straightforward. It's almost silly at times, sum of all numbers from 1 to 1, or just 1. There's nothing to add. So, how's that part? That part makes sense? Establishing the base case. Any questions on this? So the second step, the induction step, this is where we assume that our proposition is true for some natural number k. So that means assume that sum of all natural numbers from 1 to k equals k times k plus 1 over 2. So we assume that we actually have that. So we need to show that it's true for the next step. So we need to show that summation as I goes from 1 to now k plus 1. So you see, this is what I mean by the next step. So we increase k by 1. So let's think about what this should equal to. What we need to show, now remember how this formula works. No matter what this upper number is, we need to take that number, right? This is what this formula says. Whatever this is, it goes here, and then the same thing plus 1, right? That's what this formula says. So if I go back here, so it says, whatever this thing is, it goes here, so that's k plus 1. And then whatever this thing is, I need to add 1 to it. So I get what? K plus 2 over 2. So this is my goal. Somehow, I need to show this statement. So I'm going to do some mathematics here. I need to show that this equals that. Okay? Assuming that the sum of up to k actually works. So this is how we're going to write it out. And this is not the unique process. It's just depending on the problem. And by the way, I'm really working hard to make the induction proof of that divisibility by 8. So the algebra there is a little shady, but I'm getting close. I had to raise things like n plus k plus 1 to the power 5. That's messy because remember we have that n to the power 5. So I assume it's true for k to the power 5. And so k plus 1 to the power 5 is messy. But base case worked because we checked the base case. The base case was 4n equals 3. Remember that? For that problem, when you plug in 1 or 2, you get 0, so that's trivial. You plug in 3, you get some number, it's divisible by 8, so you got that. Then you assume it works for k, then you show that it's true for k plus 1. I'm stuck on that part because I'm getting a very long polynomial in the end. Anyways, so here's the proof. I'm going to take this thing, so what is this really? This is 1 plus 2 plus 3 all the way. What is the last number in our sum? K plus 1, right? What is the number before k plus 1? K. Did you hear that? If I just list them all out? Well, this thing right here is the sum of everything from 1 to k, right? So I can actually rewrite this statement as summation as I goes from 1 to k plus k plus 1. Do you agree with that? Because I know a lot about this part. This is my assumption. I know that this equals 2k times k plus 1 over 2, right? I know that this thing in the box, this is my assumption. I know that that's true, so I can actually replace that sigma with k times k plus 1 over 2 plus k plus 1. Right? This is where I'm using my assumption, that it's true for k. Well, now the rest is just algebra. I need to add two fractions, so I need to get the common denominator. So it's k times k plus 1 plus 2 times k plus 1 over 2. Right? I do this 2 over 2 trick. Is that okay? Just adding fractions. Now in this numerator, I have a common factor of k plus 1, k plus 1, k plus 1. I can factor k plus 1 out, leaves me with k plus 2 over 2. Right? Isn't that what I wanted to show? This is exactly what I wanted to get. Right? I had to show that this thing equals k plus 1, k plus 2 over 2. And this is what I have. This thing equals k plus 1, k plus 2 over 2. So I'm done. QED. Yeah. So I think it's quad erratum demonstrandum, which as needed to be shown type of thing. Isn't that a cute way to prove things? Again, the logic works because now all we have is true for 1, then it's true for 2. It's true for 2, then it's true for 3. It's true for 3, then it's true for 4. It's true for 4, then it's true for 5, and then you just loop it through the entire sequence. Well, no. We have to be careful because again, Dalton proved that if you go to infinity, you get -1/12. That's a different story. I mean, if you go to infinity, you get infinity. I mean, you add infinitely many positive integers. So that's what in Calc 2 you're going to call a divergent series. It diverges to infinity. But if you just slow down, you go from 1 to whatever largest number you can think of, as long as it's fixed, you can get a sum. It's going to be huge, but it'll get there. So how's that? Does that make sense? Two-step process. First step is usually easy. Second step, you can get really boggled in there.
What's like a question now that would use?
Well, again, like proving things like that, where first of all, it's really helpful if your variable is limited to at least natural numbers. I mean, if your variable, so that will what we call a discrete variable. So it's either 1 or 2 or 3, so there's large gaps between allowable values. If you allow the variable to be continuous, meaning like, fractions or rational numbers, that probably won't work, because then this kind of incrementation does not work. But let's say, again, this is what, let me show you. What is our problem? N cubed minus, no. It was n to the power 5 minus 5 n cubed now. Yes? Plus 4n? Yeah. The one we were trying to prove divisible by 8.
Yeah, n to the 5th minus 5, n to the 3rd plus 4.
Right? So this does not have any sigma notation, but at least all I know that n is a natural number, right? So, and remember how it works. Like if n equals 1, you plug in 1, you'll get 0, right? It's 1 minus 5 plus 4 equals 0, clearly divisible by 8, right? You can use that as a base case, but it's almost cheating, right? We won't even consider in that case. We said, n equals 2 was the same thing. If you plug in 2, you'll get 32 minus, what is, minus what? Minus 40 plus 8. That's also 0. That's divisible by 8, right? So we kind of ignore those two. I mean, you can use that as a base case. 8 is divisible by 8, good. But that's a little shady. So if I do n equals 3, if I plug 3 in there, so that's 3 to the power 5, it's 243, minus 3 cubed is 27 times 5, 135. Is that right? I believe so. Plus 12. So that comes down to be 120. Is that right? Yeah. And 120 is divisible by 8. 15 times 8 is 120, right? Right? So that's our base case. Sometimes it might take you a few steps, but this is the base case. Now to do the induction step, and this is, I'm still working on it, but I'm just kind of giving you the idea. So assume that the statement is true for some k. So that means 8 divides k to the power 5 minus 5k cubed plus 4k. We need to show that 8 divides k plus 1 to the power 5 minus 5 times k plus 1 to the power 3 plus 4 times k plus 1. So 8 divides that. So that's the next step. You increment k by 1. And that will involve some algebra. You know, we have to, well, that's what maybe there is a slicker way. I haven't actually thought of it since last Wednesday. But, you know, you open up the parentheses, you combine like terms, maybe you'll get something out of it. Actually, if you do that, if you open up all the parentheses, combine like terms, this statement will show up. You'll get those 3 items. So you can actually say, well, those are already divisible by 8. So it comes down to proving that the rest of this junk is divisible by 8. But the rest of the junk is rather huge. Maybe you'll have to run another induction on that. It gets a little too messy. Okay? So that would be one of the examples. Okay, so every time you're trying to prove that something is true for a large number of, for large values of your variable, usually infinite, and your variable is discrete, has the smallest value, and gets incremented in a nice way. Okay, you can use that. Yeah. Is that okay? I mean, I'm not going to continue that because I didn't get anywhere nice with that, but this is another example where we don't have a sigma. And actually, I do have a proof that I'll do later about the divisibility. We'll prove that something is divisible by something else. So let's try this. So, you know, not done yet. No QED. Let's try this. I want us to find the sum of the following fractions. 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4. What do you think the next one is? 1 over 4 times 5. So in general, I can express each one of them as 1 over n times n plus 1. Right? Is that okay? So if I use the sigma notation, I can just say this. It's a sum of all fractions of the form 1 over I times I plus 1, where I goes from 1 to n. This is a concise way of doing this. So really, like, it just says find the sum, right? So I don't even know, is there a special formula for that? How to do that? Maybe there is a special formula. So what you want to do, you want to actually start plugging values for n. N equals 1, see what you get. N equals 2, see what you get. N equals 3, see what you get. And maybe you'll notice a pattern that all the sums follow the similar pattern. So if you recognize the pattern, you'll say, well, it looks like the sum equals blah. Then you need to prove that, in fact, the sum equals blah, and most likely use induction on that. But the first step, we'll have to guess what the sum is. So here's the guessing part. Plug in a few numbers, n equals 1. So if I do that, if the summation of all items of this form from 1 to 1, you'll just end up with 1 over 1 times 2. Right? Just plug in 1 in there, and then there's nothing else. Right? You stop at 1. So you just get 1/2. that okay? If you do n equals 2, it is a summation from 1 to 2 of 1 over I plus 1. So you get the previous result all the way to 1. You get 1 over 1 times 2 plus I increments to 2. You plug in 2 in there, you'll get 1 over 2 times 3, right? So this is where I was 1, plug in 1, increase by 1, plug in 2, you get that. So you get 2 items. So it's 1/2 plus 1/6. So what's that? Find the common denominator. You get 4 over 6. Right, you multiply first by 3, so that reduces to 2 over 3. Is that okay? So again, we're just experimenting. We're hoping to see a pattern. Maybe some of you already kind of see a pattern of sorts, but let's just do n equals 3 just to make sure that whatever we notice stays consistent. So I goes from 1 to 3, 1 over I plus 1. So if I plug all that in, again, I equals 1, you get 1 over 1 times 2, plus. Increase I by 1, you get 1 over 2 times 3. Increase I by 1, I equals 3 now, it becomes 1 over 3 times 4. Is that right? Now, I know the sum of the first two. That's my previous step. I know the first two add up to 2/3, right? I know that much, so I can actually expedite the process. Write it as 2/3 plus 1/12. Do the common denominator. Common denominator is 12, so multiply the first fraction by 4. So that becomes 8 plus 1. 9 over 12 reduces to 3/4. So 1/2 when you start at 1. 2/3 when you start at 2. 3/4 when you start at 3. What is the pattern? That's what it looks like, right? The numerator is whatever value of n is, denominator is increased by 1. Isn't that the pattern? So this is our guess. So our guess, that equals to n over n plus 1. This is nothing but a guess. But just to make sure you understand our guess, this means now if I ask you what is the sum from 1 to 10 of these guys, you will say 10 over 11. Hopefully. This is the guess, right? So now we're going to do the induction to show that. Now, the good news, we already established the base case a few times. I mean, this is the base case, n equals 1. We showed that that's true, right? So base case is established. Now we're going to assume that this statement is true for some k, and then you need to show that it's true for the next value of k. Does the plan make sense? Okay, so the proof. So again, we're trying to prove that. We're trying to prove that this equal to n over n plus 1. So the base case for the base step or whatever. So we already established that. So n equals 1. So the summation I goes from 1 to 1 of this equals 1 half. So it checks out. And again, at times, it will feel very silly to check the base case. Like, this is a very silly thing to do, and it should feel like that. You know, it's okay. The base case should feel very simple, sometimes silly, makes you smile a little bit, how silly it is. That's okay. The induction step, that's the one that's supposed to make you cry, because that's the hard one. Okay? So again, we're going to assume that our proposition is true for some k. So assume that the proposition is true for some k. Meaning the summation from 1 to k of 1 over I times I plus 1 equals k over k plus 1. Okay? And again, it's not very stretched assumption because we showed that it's true for some case. Right? That's the base case. Now we need to show that the proposition is true for k plus 1. Meaning, we're going to show that the summation as I goes from 1 to k plus 1 of I over I times I plus 1 equals what? What do we need to show? Over k plus 2. So whatever this value, that's the numerator, denominator is greater by 1, right? That's the general pattern. Whatever the limit of your k, that is the numerator. So whatever this thing is, that's our numerator. Denominator is greater by 1, so k plus 2. Then if we're able to show that, then we prove the induction step and we're done. Okay? So this proof, the rest of this proofs will look very similar to the one that we just did. And most of the sigma proofs will look like that. Yeah, let me go back and I'll talk a little bit about what happened in the previous proof. Not in this one, in this one. Because usually when you play with the sigma notation, because that's addition, you can always take your addition to k plus 1 and rewrite it as the addition to k plus that k plus first step, that last added or whatever. Because the way the sums work, you're always going to get first k things laid out. So that's this, right? So I can always do that. Plus that new step that's given by k plus 1. You do that? It's because this is the way the addition works, just basic addition. So that means I can take this expression that I'm trying to prove, summation as I goes from 1 to k plus 1 of 1 over I plus 1, that equals to the sum of the first k steps, so that's I goes from 1 to k, plus the k plus 1 step. So if I plug k plus 1 for every I, I'll get 1 over k plus 1, k plus 2. Do you agree with that? If you plug in k plus 1 for every little I, that becomes k plus 1. That becomes k plus 2. Is that okay? So again, you get the first, 1/2 plus 2/3 plus whatever we got there, and then plus that new extra step. And again, the reason why this is helpful, because this is our assumption. I know what that equals to by our assumption, and then I'll just have to add a few fractions. Because by our assumption, I can replace this statement right here with k over k plus 1. There's the assumption, right? But this is true. So this whole thing becomes k over k plus 1 plus 1 over k plus 1, k plus 2. Is that all right? So again, this thing is the first k steps, and this is that new extra one. Now I just have to add two fractions. So how do we do that? What is the least common denominator? K plus 1, k plus 2. That means I'll have to take the first fraction and multiply it by k plus 2 over k plus 2. That will get them to the least common denominator, plus 1 over k plus 1, k plus 2. So this becomes k times k plus 2 plus 1 over k plus 1, k plus 2. Is that okay? Because at this point, I'm just adding fractions. We had to multiply by k plus 2 to get them to have the same denominator, right? Are we okay with that? So now let's simplify. Distribute k, so that's k squared plus 2k plus 1 over k plus 1, k plus 2. That numerator factors in a very nice way, right? The numerator is a perfect square, actually. The numerator is k plus 1 squared. If you don't see the perfect square trinomial, you need two numbers that multiply to 1 and add to 2, so that's 1 and 1. So that's our square over k plus 1, k plus 2. So we can reduce. We can reduce this fraction by k plus 1. So we got k plus 1 over k plus 2. Isn't that what we wanted? QED. How is that? I mean, this is algebraically heavy, and you have to be a little adventurous to do those things. Just don't be afraid to just start writing. Because all you have to do is just start. Just know the plan. Know the plan that you need the base case. That's usually easy. And then you make your assumption, which is basically your original statement. And then you just have to prove that it's true for the next one. And then that's where you just see where it takes you. Some of the tricks that you notice with the sigmas, you can always do that split. When you do the sigma for k plus 1, you can always do the sigma for k plus the last step. And the sigma for k is usually your assumption. Okay? So that's what allows you to plug that assumption in and then do some arithmetic to get to whatever it is you're going. Any questions on this? not fun?
So this is one factor.
Well, yeah, you have to be pretty solid with your basic algebra and arithmetic and those things. Like, you shouldn't be hung up on the places like, what is the LCD? That's supposed to make you happy. Oh, this is the easy part. Just bend. The stuff before that's logically challenging, but is that all right? Let's do one more. Without sigma, one of those division problems. Prove, and this is a really fun one, that 133 divides 11 to the power n plus 2 plus 12 to the power 2n plus 1 for all natural numbers n. So 133 divides that unholy mess regardless of the values of n. Okay? So this is not the case where we can try the induction. I'm not saying there could be many ways of proving that. Sometimes induction works better than other ways. Because again, the all natural numbers, that's the key, because it allows us to establish the base case. Because what is the smallest value n can be? 1, right? Because n is any natural number starts at 1, so that's my base case, n equals 1. Let's plug in 1, literally plug in 1, and see whatever we get, is that divisible by 133. Okay? So we're going to try to prove by induction. So first establish the base case. So that means n equals 1. So we need to show that 133 divides what? 11 to the power 1 plus 2 plus 12 to the power 2 times 1 plus 1, right? Right? So what is this? This is 11 cubed plus 12 cubed. Is that right? I mean, at this point you can plug that in a calculator. That's a little big, right? You can actually do something very cute. Because we tend to leave our calculators at home and things like that. This is a sum of 2 cubes. Did you hear that? There is a sum of cubes formula that allows us to factor something like that. And these are the formulas that you should be familiar with. I teach this formula in Math 099. So that's a cubed plus b cubed equals a plus b, and then a squared minus ab plus b squared. This formula allows you to factor the sums of cubes. You have a very similar formula for the difference of cubes. Which is a cubed minus b cubed equals a minus b, and then a squared plus ab plus b squared. I usually give those formulas on the exams. You don't have to have them memorized, but you need to know that they exist, and sometimes you kind of have to use them. So in this case, I like using those formulas. It allows you to compute things faster. So if I apply the sum of cubes formula here, the value of a is 11 and the value of b is 12, right? A is 11, b is 12, so then it becomes 11 plus 12, and then 11 squared minus 11 times 12 plus 12 squared. So this becomes 23 times 121 minus 132 plus 144, right? So actually it's 133. The whole thing in the parentheses is 23 times 133. Right? Is that divisible by 133? Yeah, I mean, that's by definition. This number is 133 times something else, so it's divisible by 133, right? Therefore, divisible by definition Is that okay? I mean, you could have literally go 11 cubed plus 12 cubed, boom, divide by 133 equals 23, therefore divisible by 23. But this is a little slicker, using some wonderful properties of natural numbers. So we just established the base case. That's basically the long story here, right? We plugged in the smallest value n can be, and then we showed that at that step, 133 divides that big number. Okay? So we've done that. Now we have to establish the induction step. So assume that 133 divides that number for some k, and then show that it's also going to hold for the next value of k, which is k plus 1. Oh my god. It's going to get a little funky in there. Okay? But let's try it. So induction step. So assume that the proposition is true for some k. And again, k is a natural number. We don't even have to specify that because we're just messing with natural numbers. Okay? So meaning 133 divides 11 to the power k plus 2 plus 12 to the power 2k plus 1. Okay. All right. So that's assuming that we need to show that the proposition is true for k plus 1. Meaning, we need to show that 133 divides 11. So I have to replace every k with k plus 1. That's basically what I'm doing. So I have to be really careful here. So if I replace k with k plus 1, I'll get k plus 1 plus 2. I'll do the sum in a little bit. But this is what I'm doing. I'm replacing every k with a k plus 1 plus 12 to the power 2 times k plus 1 plus 1. See what I did? For every k, I place k plus 1. Now I'll simplify that. So it's 133 divides 11 to the power k plus 3. Right? If you combine, 1 plus 2. And in another one, it's 12. So it's 2k plus 2 plus 1. So it's 2k plus 3. Is that okay? So this is what I need to show. I need to show that 133 divides that statement. So I'm going to start messing with that statement. Okay? Till I can conclusively say it's divisible by 133. And of course, at some point, I'll use my assumption. There's my assumption. It will come into play at some point. Okay? So really, what you want to do, you want to algebraically manipulate this expression till it looks like the expression in your assumption. Because you're going to have to use your assumption at some point. So let's start messing with that. So I have 11 to the k plus 3 plus 12 to the power 2k plus 3. Now, in my assumption, I have 11 to the power k plus 2. Right? So by the rules of exponents, I can rewrite 11 to the power k plus 3 as 11 to the power k plus 2 times 11. Do you agree with that? By the rules of exponents, I can do that because we add exponents, so you get your k plus 3, right? Okay, so you see I'm trying to match. I'm trying to get the same exponents. Now, for 12, I have 2k plus 1. Here I have 2k plus 3. So that means I should probably rewrite it as what? Because again, I'm trying to get my assumption in there somehow. Right. Right, 2k plus 1 or times 12 squared. I can do that. Is that okay? All right. So this is where I'm at. Let me write it like this. So it's 11 times, I'm going to write it 11 times k plus 2 plus 12 squared is 144 times 12 to the power 2k plus 1. Okay? Because 12 squared is 144. And now I'm going to do something very sneaky. Something sneaky, sneaky, sneaky. Because look, if I try to express 144 as a sum of two numbers, one of which is 133, what do I get? 144 is 133 plus 11, right? So I want 133 because that's my division thing. And 11 is going to play nicely as well, because look what happens. Do you agree that that's the same as the original statement? That these two add up to 144? Is that right? Now, the reason why I'm doing that, because look, here's this part. If I factor 11 out, I'm left with 11, k plus 2, plus 12, 2k plus 1, right? And what's left? 133 times 12 to the 2k plus 1. Am I done? Because look, almost. I mean, I don't have to do anything else. Is this divisible by 133? By definition, it's 133 times something, so it's divisible by 133. Well, is this divisible by 133? This is my assumption, right? By assumption, 11k plus 2 plus 12, 2k plus 1, that's exactly what that is. This part is divisible by 133 by assumption, right? So this, divisible by 133 by assumption, divisible by 133 by definition. So is the sum divisible by 133 then? Yeah, that's one of our properties. We've proven that before. Therefore, 133 divides, all that. 11 to the 2, 11 to, what was that? K plus 3 plus 12 to 2k plus 3. So QED? It's a little tricky. You had to mess with the numbers there at the end. So yeah, this one is a little messy. But again, the logic was, one way to think about that split of 144, you knew you needed to use your assumption, okay? And the only way you can use your assumption, because you have the 11 here, so if you get 11 there, then you can do some factoring and then you get your assumption here. Well, just luckily, if you pull 11 out, you're left with 133. So that's another way you might stumble onto the solution. Like, oh, well, that's just perfect. It's 133. I don't need to do anything else. Right? Is that fun? Okay, I think we have a little bit of time left to do that divisibility by 3 case. It's not induction proof. It's very fast. We don't need to do much there. And actually, it will do divisibility by 3 and 9, because those are very similar, right? Remember how we can tell whether the number is divisible by 3? How do we do that?
If you add up all the numbers, it's divisible by 3.
Right. If the sum of all digits is divisible by 3, then the number itself is divisible by 3. Same thing for 9, right? If the sum of all digits is divisible by 9, then the whole number is divisible by 9. So divisibility, wow. Is that right? Is that how you spell divisibility? That many I's? By 3 and 9. So I'm really just going to do kind of a one case. I'm just going to say, well, let's pick 5-digit number or 6-digit number, because we can do it for all like kind of an induction argument. Okay? You can do like a base case, like a 1-digit number. So that's 309, right? 3, 6, 9, right? If you look at the number 9, is the sum of all digits in number 9 divisible by 3? Yes. Is 9 divisible by 3? Yes. So that's the base case. But then you're going to look at a 2-digit, 3-digit, 4-digit, and so forth. I'm just going to show you how to do like any one of those cases. So let's consider a 5-digit number. So let's say n equals A, B, C, D, E, like we did before. So this is a 5-digit number, right? So basically I need to show that if 3 divides n, then 3 divides the sum of A plus B plus C plus D plus E, and vice versa, right? It's kind of that. So I'm going to do the following. I'm going to use our base 10 notation. I mean, if you understand how the base 10 works, like for example, don't write this down, but if I give you a number like that, here's a 5-digit number, can you say that number to me? How? No, you can 24,746, but that really means you have 6 units, 4 tenths, 7 hundredths, 4 thousandths, and 2 10,000ths. Right? This number in base 10 is written like this: 2 times 10 to the 5th plus 4 times 10 to the 4th plus 7 times 10 cubed plus 4 times 10 squared, right? Plus 6 times. No, what? That's not right. What am I missing? 5, 4, 3, 2, 1? That's not right. Oh, yeah. 4. That's better. Sorry. I don't need 5 zeros. 5 zeros is 100,000, right? So it's 4, 3, 2, 1, 10 to the 0, right? That's base 10. Or it's 2 times 10,000 plus 4 times 1,000 plus 7 times 100 plus 4 times 10 plus 6. That's base 10, right? Is that okay? So I can do that with my A, B, C, D, E. So that means A, B, C, D, E is A times 10,000 plus B times 1,000 plus C times 100 plus D times 9 plus E. Right? D times 10, very good. I don't know where 9 comes from. I'm one step ahead of myself because it will be 9 there in a minute. Very good, thank you. Is that okay? Now I'm going to do this. I'm going to, instead of writing A times 10,000, I'm going to write A times 9,999 plus A. Is that the same as A times 10,000? Yeah, so I'm going to do this for every one of those. Plus B times 999 plus B plus C times 99 plus C plus D times 9 plus D plus E. I mean, I can do that, right? There's nothing wrong with that. I'm still have my original. This is my A's and 9's look very alike here. This is an A. This is an A. So look what happens. I'm going to rearrange this statement. I'm going to write all the 9's first. So A times 999 plus B times 999 plus C times 99 plus D times 9 plus A plus B plus C plus D plus E. Right? I mean, I just rearranged things. Is that okay? Now look what we get. This part right here is divisible by 3 no matter what. Do you agree with that? Because each one of those is divisible by 3, all those 9's. Right? And this statement in the box is divisible by 9 regardless of A, B, C, D, and E. Do you agree with that? This is divisible by 3 and 9 regardless of the values of A, B, C, D, and E. So no matter what A, B, C, D, well, there's no E even, but A. So then it's all going to be about this last parenthesis. Well, this last parenthesis is the sum of all digits, right? So if the sum of all digits is divisible by 3, then the whole thing is divisible by 3. And if the sum of all digits is divisible by 9, then the whole thing is divisible by 9. And vice versa. If the whole thing is divisible by 9, then this must be divisible by 9. Because that's already divisible by 9. And if the whole thing is divisible by 3, then this has to be divisible by 3. So that's where that rule comes from. Because it's all about this last thing. So if this is divisible by 3, then the whole thing will. And if this is divisible by 9, then the whole thing will be divisible by 9. Isn't it? Fun? This is only 5-digit case. You do the same argument for all of them.
So is that like QE?
Yeah, base.
This is divisible by 9.
Regardless.
So this is the only question we have.
Yeah.
And if that equals 9.
Right. Basically, you should write a sentence. I'm tired. But yeah. But you see, because it all hang up on the sum of this, and it's precisely my digits. So if the sum of all digits is divisible by 3. So few sentences QED. This kind of summarizes what we just found. Okay? Good. Fun. So on Wednesday, we'll start talking. We're not ready to talk trig yet. I want to talk a little bit about, review some function stuff. We're going to review some function notations, domains, odd, even functions, all that fun stuff you learn in algebra, but it's important here. Okay, especially the odd and even functions. They come up a lot in trig, and usually you forget that from course of algebra. So anyways, I will see you on Wednesday or maybe in my office hours.